So in this video, what we're going to be doing is laying down some of the groundwork for proof. Proof is an area of mathematics that's very important once you get to degree level. And we lay the groundwork here. We do a little bit of it here, we do a little bit more at A-level maths, a little bit more in A-level further maths, and then once you get to degree level, being able to prove mathematical theorems is a whole part of a degree in mathematics, okay, as you really develop those ideas. So, quite often with proofs, you'll come across a statement that you may feel on first sight is quite obvious. But mathematically, we want to be able to prove that that statement is true. So it might say something about all integers, for example. So all numbers like 1, 2, 3, 4, 5, 6, 7, 8, all positive integers, let's say. Okay. And part of it requires you to be able to show that an even times an even is an even, right? So these are things that maybe we already know. We have, if you have got something like 2 times 4, then we know that that's going to be 8, of course. But on a wider aspect, you could say, well, if you have an even number and you multiply that by another even number, then this might not be something you really think about a lot or have thought about a lot, but this will always be even. Okay, so when I'm writing this down, it's fine at this stage to really write something like that down so it's written in words so you can really explain that. And of course you can check that as you go. You could try it out. 2 times 4 is 8, or 4 times 6 is 24. Okay, so we're always getting those even values. Now, why is that the case? Why would that be the case? First of all, if you have an even number, like 2 or 4, then you can write that as 2 times something, okay? Because 2 and 4, because they are even, are multiples of 2. So I would be able to write an even number as 2 times k, for example, where k is an integer. And if I had another even number, then I could write that as 2 times L. Now I've got to use a different letter there because these two even numbers don't have to be the same number. So I could have 2k and 2L. Now when I multiply these two together, I'm going to get 4, because 2 times 2 is 4, KL. And what's important is that the 4KL has a factor of 2, because I can write that as 2 lots of 2KL. So clearly, because it has that factor of 2, it has to be even. Okay? So this can be proved in general using a similar argument to that. So really what we want to know, we need to know that, and we need to be able to prove that if necessary. Okay, so what about if I had an even times an odd? So if I've got 2 times 3, even times odd, well, I know that 2 times 3 is, of course, 6. And 6 is an even number. Now, is that always the case? If I multiply an even by an odd, is it always even? Or could it be odd? Okay, well, the answer to that is that it will always be even. Now, why is that the case? Well, even, if I had an even number, I could write that as 2k, remember, just like I did before. If it's an odd number and I've got to force it to be odd, then an odd number is always one more than an even number, isn't it? Okay, so if you think about the number 3, it's 1 more than 2, and 5 is 1 more than 4, and 7 is 1 more than 6. Right? So an odd number is always 1 more than an even number. And remember, I wrote down an even number last time as 2L. So 1 more than an even number would be 2L plus 1. So I know that this would force that would have to be an odd number, where L is an integer. Now if you multiply this out, we have 2k times 2L, which is 4kL, which we had before. And then we've got 2k times 1, so that's plus 2k. Now, do you see that both of these terms have a factor of 2? I could factor 2 out of both of them. So I'd have 2 lots of kl from that term, and then divide that by 2, I'd just get the k. Now, because k and l are integers, I know that this is just going to be an integer. And because I factored out 2, I know that this has to be even. So that is proving that an even times an odd has to be even. And of course, you can flip it around the other way and do odd times even is even, and we get the same thing. Okay, so we know then, and we've proved it, that an even times an odd is an even number. Okay, so these things that we quite often take for granted, we can now prove to be the case. Now, what if I had an odd times an odd? Well, that would be like having 3 times 5. 3 times 5 is 15. Now, I recognise that's an odd number. Would I always get an odd number? Will it always be odd? Well, let's see, shall we? So from before, remember, an odd number was 1 more than an even number. So this odd number could be written as 2k plus 1. So it's 1 more than 2k. So that means it has to be odd. And this one I could write as 2l plus 1. So it's 1 more than 2l, 1 more than an even number. Now if you expand these two out, we're going to get 2k times 2l, which is 4kl. 2k times 1 is 2k. 1 times 2l, and then 1 times 1. Now, can you see that not all of these terms have a factor of 2? This one does, and this one does, but this one doesn't. So what I could do is I could write that as 2 lots of, and I could factor the 2 out of those 3 terms, so 2kl plus k, not 2k, plus k plus l. And then you've got that plus 1 on the end that I couldn't factor the 2 out of. And what does this now look like? It looks like 2 lots of some number, some integer, plus 1. So this is 1 more than an even number. So that means it has to be odd. So we now have proved that an odd times an odd has to be an odd number. Okay? So not only should we know these things here and be able to use those facts as part of a proof, those facts can also be proved themselves.